Good morning, welcome. It's morning here in Denver, Colorado. Actually, the suburb is called Centennial. I'm sitting in the Vibrant office running MEscope. And as you can see on the screen, I have a picture of the test article that we're going to talk about in this first curve fitting application. And then we have a second one where we're going to use our old friend Jim Beam again. And we're going to do some OMA curve fitting using the mode shapes of Jim Beam, and then we're going to create some cross spectra, which would simulate an OMA test, and then curve fit that data and compare it with the original mode shapes. This one is a little different. This data was collected by one of our resellers. The company is called well, it's Jim Steedman's company in Los Angeles, and they were called in to test this grate. This is Navcon Engineering. This was done several years ago, but it's a very good example of multi-reference curve fitting. So we're going a little more advanced here today and using our multi-reference curve fitting in MEscope, which is part of our advanced curve fitting option now. And we're going to look at a lot of data here that was taken on this grate. Now, I don't know all this, why it was tested. I believe they were having failure problems. This was part of a water treatment facility, I believe. And so Navcon was called in to test this grate. You can see it's been taken out of service. It's in a laboratory with a nice test setup here, and a lot of accelerometers. We'll look at some of these other pictures here in a minute. And it was impact tested, and it was impacted in 3 different directions from one of the corners. So once that is done with a fixed impact or a fixed input point, that would be the reference, and it was impacted in the horizontal X, Y, and then vertical Z direction. So 3 sets of data really were taken. 3 different impact tests done with all the accelerometers in place, and basically impacted from the X direction, the Y direction, and the Z. Let's take a look at those. Now, part of this project here is some added files, and these are JPEG files that were added in to MEscope's project. This is the project for the grate, for the grating, and these are separate JPEG files that are stored on my disk and simply referenced by this project. So when you add files to an MEscope project, you have to be careful if you move them around that MEscope may lose the reference. The best way to keep them referenced is if I do, I want to come up here to my project menu, and if I do a save project copy, and I want to copy the project to a different location, a different disk, a different folder, that command will also move the any added files, in this case the JPEGs, the picture files, and it will re-reference them so that when I open that project in its new location, it will still have them. If I manually try to move things around using Windows Explorer, I may lose the connections there. Anyway, let's go look at some more of these pictures. Here's another one. Okay, this is showing impacting in the, it looks like the, X, Y, or Z horizontal direction here with an impact hammer, a load cell on the hammer, so that we're measuring FRFs, true FRFs, so we're going to get mode shapes from this set of data. Accelerometer response to the force impact in that direction. Let's look at another one here. Okay, so here it is in the vertical direction. The impact hammer being applied to the corner in the vertical. Here's another JPEG. Okay, here it is in the other horizontal direction, and there's Jim there using the hammer. Jim Steedman. So he collected this data. You can see some of the accelerometer wires, and we'll see in a minute when we look at the model itself and some of the data that he had quite a few accelerometers on this grate to measure its response to each of these impacts. Let's look at some of these other pictures. Okay, well there's another picture showing the entire test article. Let's look at this one. Okay, another view of it. Now, I made a movie of some of the animation here, and this is a WMV, Windows Movie video, and that's been added when you make videos of the animation or MEscope. They get added in here as added files also. So let's go. This is a curve fitting session, so let's go back and look at our data. Here's a model of the grading, nice simple stick model with a little bit of surface added to it, but this is something you can build very easily in MEscope. Let's go over here and just take a look at the data. I'm going to expand. Now you can see that this measurement here, this is an FRF, a magnitude of it, and it's selected. So in order to animate shapes when I have multiple reference data like this, the animation is going to force you to select a reference. Now, how do I know where the reference is? Well, the data has been labeled with the DOFs. This is the best way to do the bookkeeping on your measurements. Not necessary, but the simplest and easiest way to do the bookkeeping on your measurements. So you can see that the ones that are selected are all with respect to reference 1 in the Z. So I'm just guessing here that's the impact point, and the X direction, the X direction was the reference that's selected. And then I also have Y direction and Z direction data, but I can only animate one from one reference at a time. So you can see this is a rather large set of data here, 233 FRFs, or measurements as we call them, and there's points that are numbered up to 80 here. Not necessarily in order, but this data has all been linked up with the model. Let me put this back over on the side, and I'm going to pull my line cursor down here to one of the lower frequencies. Let's just zoom in here a little bit down at the low end and see what we have. This is where I like to go before I do any curve fitting. You can see a couple of peaks down here in the data. I'm going to start the animation, and this is ODS data now. We're just animating data at the cursor location. And what I want to do is just look, this is a lot of data, so I want to go down here at one of these peaks and put the cursor on there and see whether I have a good set of data. And this is rigid body motion, what I'd call rigid body motion. This is the grate just moving around on its base, whatever it is. Think of it as a mass on a spring, and that's a pretty good indication that, at least in the X direction, this X direction set of data looks pretty good. Now if I move it to that other peak, not so good. Now how do I change the animation to look at a different reference? If I start the animation, let me stop this and explain that. I'm going to unselect everything. Now I've got all the data unselected. If I start the animation, it's going to say, wait a minute, you've got multiple reference data. Select a reference DOF. So I'm going to say OK, and now it puts up the selection box, and it's got it already pointed to reference DOF, and you can see I've got 3 references here, 1X, 1Y, 1Z. We saw that in the data. So if I switch over here and select the Y direction, that doesn't look very good either. Let's just look at the Z direction. Not very good at that peak, but let's just move it over here to the other peak. So the first peak there is not really giving us a very good indication of rigid body motion. There's a good indication, but their Y direction is very clean. So the Y direction is exciting that structure, horizontally. Z direction, not so good. However, with multi-reference data, we can still say, we got some pretty good data here, because we don't expect necessarily the rigid body motion in the Z to show up, depending on, the mounting. If the mounting was more like a spring in the Z direction, then I would see a nice clean Z direction motion. But I'm seeing good X direction motion. I'm seeing good Y direction motion here down at the low frequency. So that's an indication that I have a good set of data. Whenever you take a lot of data like this, you really want to, well, I closed my selector, so let's go back now and start this again. And I'm going to put the selector up. Now let's go look at a resonance. Well, here's one out here. So that resonance is, I'm just going to set my line cursor on there. Now we have a peak cursor. That's a good way to zero in on a peak also. There's my X direction. Now that certainly looks like a believable mode shape. Let me go to the Y direction. Still same mode shape. So if I switch references and I still see the same mode shape, that's an indication of a resonance. If it changed on me, that's an indication of an ODS, not a resonance, maybe more than one resonance. There's a Z direction, not bad, still the same, although the Z, because of the dominant motion of this mode, it's mainly a horizontal mode. Let's go to a different peak here. Let's go to this peak. Okay, a very similar looking mode. It hasn't changed a whole lot. There it is. It is a different mode shape in the Y direction. Let's go back to the X. See, it's changed on me, so maybe the X direction data is not accurate. There's the Z direction. So now I've got two references that are giving me the same operating deflection shape and the same ODS. And what we can conclude is that ODS is being dominated by a resonance, because no matter whether I go Y or I go Z, Z is different. X is different. So that one may be problematic. This is where when we go into a curve fitter, we're going to get a confirmation from the curve fitting. Now there is another peak. There's what looks like a mode to me. There's the Y direction. It hasn't changed a whole lot. Let's look at the Z direction. Well, this is a Z direction mode. So there, clearly I have a mode shape where, regardless of the reference, that mode is dominating the ODS in all three directions. Let's try one more, and then we'll go into curve fitting, and we'll see what the curve fitting will do for us. Now, as we go up in frequency, the shapes get more complicated. I don't want to say complex. We use that term differently. These are complex shapes, but the phases, now here, another clean result where the Z direction is not showing a very good mode shape, something similar, but the Y clearly dominated by a horizontal resonance, and the X, same thing. So this is where you want to start any kind of curve fitting, and when you have multiple reference data, one of the advantages is that you can do this kind of a test, just looking at ODSs to decide whether is that a resonance or is that just order, what we call an order based or order excited, or I've just got some energy coming into the structure at a particular frequency because it's a running machine, and it may be exciting a resonance, may not, may be exciting several resonances. looking at this ODS data will start to give us a clue about what we're looking at. Let's go into curve fitting. So I'm going to open up the curve fitter. Now I want to, this is a multi-reference set of data, so I want to unselect, and I'm going to go in and I've got it zoomed in here, so let's zoom all the way out. So here's my data. Now the first thing in curve fitting, this is lightly damped data, so we can use the quick fit. But we're going to use a multi-reference. You can see that automatically the mode indicator has looked at the data and it's selected a multi-reference CMIF mode indicator for us. Let me turn off the cursor there for a minute, and I'm just going to press the Count Peaks button. Typical FRF data, when it's an accelerometer over force, we want to look at the imaginary peaks. Those are the sharpest peaks. And here's what we get, something with just a lot of peaks in it. Best place to start curve fitting is down at the low frequencies. I can count 1, 2, 3, 4, there's 5 modes here. Now the indicator is counted 83 peaks, and those are the ones above this threshold here. But let's just go down and zoom in and start the curve fitting. I'm going to get my zoom tool here and just select this amount. Now it doesn't get any cleaner than this. Nice, clean, single peaks. Now this is a multi-reference, as I said, mode indicator. If it was truly repeated roots or closely coupled modes in this data, we would see 2 peaks in the vicinity of one of the resonances. But here the indicator is just showing us 1 peak for each of these 5 modes. So I can go ahead and do multi-reference curve fitting. And what's going to happen is, well, let me just go ahead and do it and we'll see what it looks like. I'm going to go and use the quick fit. This is my favorite curve fitter. When I have data that's lightly damp like this, always start with a quick fit because that is the easiest and it's the quickest. Okay, it says curve fitting error, frequency and damping. That's interesting. Oh, see, it's got too many peaks here. Let me count the peaks again and see. Okay, 5 peaks. It was trying to curve fit all 83. Even though I had zoomed in here, it still said, hey, you got 83 peaks here, and that curve fitter doesn't work well with that many peaks. So here it is with 5 peaks, and you can see that it's got, there's a fit function laying on the data. It's gone through and it's fit all of my measurements. How many of them? 80 of 233. So we curve fit all 233, and the fit function is laying on there pretty well. You can see that in some of these measurements, depending on the reference, we don't have a good measure. But again, here's what the multi-reference fitter has told us. It's telling us not only that it curve fit these modes, and we'll look at the mode shapes in a minute, but it's telling us the participation of each of the modes in each of the references. So let me expand this so you can see it a little bit better. In the first case here, the first mode at 16 Hertz, let me just clean this up a little bit so we can, oh, got the wrong one. I'm going to reset the column here so you can see it a little better in the spreadsheet. So here's the results of the curve fitting on one of the measurements. The residues are going to change, frequency and damping. This is a global method. I used the multi-reference polynomial and then the multi-reference residue polynomial fitter. So it went through, quick fit will go through and use these 3 fitters and show us the result. It's done all that, but the interesting part with multi-reference data is it's the first thing it does is look at participation of each of these modes in each of the references. So this first one is saying that the first mode is dominant in the Z direction. The second mode is 80% in the X, 50% in the Y, and not in the Z. So this is showing us where these mode shapes dominate the ODS. Remember, the FRF, you can think of the FRF data as an ODS at any frequency, normalized by the force, of course, in this case. Third mode, dominated in the Y. Fourth mode, dominated in the Z again, and then the last mode is dominated in the Y. Well, let's just go ahead and look at these mode shapes now that the curve fitter has pulled out of this data, and see if in fact it matches up with. So I'm going to put this back over here, but let me just slide this over, and I'm going to animate right out of the curve fitting data. So I can do that here when I'm curve fitting, and up here is, it says curve fit, shapes, animate shapes. Let's start that curve fit. Again, I can't animate all of my mode shape data because it's multi-reference now. It matches up one for one with my FRFs. So I need to go ahead and set up a reference, and there is the first mode animating in the X direction. Now the curve fitter is going to curve fit data based on these participation. It's going to weight the data and curve fit, so it really got this mode shape from the Z direction. The X and the Y data was pretty much ignored, but when I go to animate the shapes, it's going to give me a good shape in all three directions, because the curve fitter said, hey, I use mostly the Z direction to do the curve fitting, very little of the X and Y, and now I have a nice clean bending mode or torsion mode of the grate at that frequency. Let's go to the second mode. Now the second mode is a combination. It's 80% X and 50% Y and a little bit of Z. So here it's ignored the Z direction, which is what it should have done, because there's very little participation of this mode in the Z direction. Now when I select Z, I'm going to get a nice mode shape for all three directions, because that's what the curve fitter is going to do for me. Let's go to the third one. Now this third one is going to be primarily a Y mode. There it is. We saw that kind of in the ODS data, I think from the X and Y, but now we have a clean estimate of that mode shape from our data, because the participation was mainly in the Y direction. Next mode here, this fourth one, is going to be a Z direction mode. Again, like the first mode, and there it is, Z direction. You can see it's the same mode shape regardless of which reference I choose. Final one here is a Y mode. There it is. So we're getting a little bit higher bending, higher, what we call, well, certainly higher frequency, but we'd call that maybe second bending in the Y direction if we want to give it a name. Again, this is what the curve fitter can do for us, because it's figured out, you know, from the data which direct what participation was the strongest. Let's go back now and divide and conquer. Again, this is the best way to do curve fitting, especially when I'm using a curve, when I'm using the quick fit. So quick fit, you can go through and actually fit modes one at a time if you want to. We've just done 5 of them here at a time. Now let me put the, well, let's just go back, and I'll go back and put the mode indicator back up again. So yes, and let's, so here's another clump of modes in here, another frequency band. Let's just go back in and set our band right here. And so there's 7 modes. See, it's told me there's 7 peaks here. As I interact with the mode indicator, and I move the cursor band, it's going to count the peaks in the band. And those are all clean modes. Let's zoom in here. When I mean clean, there's no repeated roots or multiple peaks at a given frequency. That's the other thing we can do with the multi-reference fitting. And we may not get to an example of a repeated root or closely coupled modes today, but here I got a nice clean peak for each of these resonances. There's the seven peaks. I'm going to go ahead and do the quick fit again. So let's just do a quick fit. And bingo, the fit function's laying up there on the data. And as I scroll through how many measurements do I have? 233 of them. The quick fit did a decent job, what I would certainly call acceptable in terms of the fit function laying on the data. Now, again, we want to go look at those mode shapes, and we can see we got 7 additional modes in here, and they all have different participation in the FRF data or in the ODS at each of the frequencies. So let's go back. Let me put this over to the side, and I'm going to start the animation here again. Animate shapes. Again, it's reminding me I've got multi-reference data, and I can only animate from one reference at a time. And so there is mode number 6. So that's my new curve fit result. And it's primarily an X direction mode. So I'm animating in the X direction. You can see there's some strange things going on at the end of the grade there, but not really. Given the data that we took on this, let me put the point numbers up. There's point numbers and transparent background. Let me switch over to an opaque background. I'm going to turn off this transparent background here. So there you can see quite a bit of data. Those are all the test points on this grading, and really no interpolation needed for unmeasured points. All the points have been measured in this particular model. A little bit of complexity there. You can see that in the mode shape. I could remove some of that by using the Normalize command. Under Animate here, there's a command called Normalize the shapes. That would make it behave as what we call a normal mode, with all the values are plus and minus 1 in the mode shape table. Here we're animating right off of the curve fit data, so this is just being converted as it's presented for animation. But again, the curve fitter has given us the same mode shape at each reference. So once I've gone through this multi-reference fitting, let's go to the next mode. This mode is mainly a Y direction mode. And so there it is, Y direction. If you look down here in the XYZ coordinates there, that mode is at least the data that we took is dominating in the Y direction. Here's a Z direction mode, -1 in the Z. And sure enough, there is a what I'd call second torsion. It's a twisting mode, but it's more complicated in terms of the twist. If I go back here to the first mode, there's first torsion. If I go up here to number 8, there's second torsion. Number 9, this again is Z mode. Boy, we don't have a name for that. We certainly have its frequency. And so we can always identify the modes by their frequency. But this is, maybe you call it an oil canning of this grate, kind of an oil can mode. Here's a, what is this mode? This is another Z mode. A little bit strange as we get up into the higher frequencies. Maybe we call that second bending. The curve fitter has done what it's done. Now maybe I could tweak the curve fitter a little bit, play around with it a little bit. Here's a nice clean mode. And finally, another mode. These final three modes, you can see the structure is starting to deflect or deform primarily in the vertical direction. So all these modes, even though we tested in the X and Y, well, here's one that's 80%, 80%. So it's moving in the Y. Obviously, you can see that there's some bending of the edges, as well as plenty of deflection in the Z. Let me turn the points off again. There it goes, much faster now. So you can see what multi-reference curve fitting does for us. It just gives us more information about how the modes participate in each of the references of data. And really not very much extra work. Where we go back and if we look at one of the pictures here, you know, this was just, that's not the one I wanted to show, but impacting in each direction. Here we're impacting in the Z, and then we have a picture of impacting in the Y and the X directions also. So not a lot of work once you're all set up and you have enough accelerometers and enough channels in your acquisition system to do an impact test like this. Now, if you didn't have, I mean, you could do this with a 4-channel system. These are triaxial cells. How do I know that? Well, I've got motion in the X, Y, and Z at each point. So that's another way to make sure that you're going to measure the resonance motion, dominant motion in all 3 directions. Let's go to the next project. We're using up half of our time here already, so I want to go. I'm going to close this project, and I'll close it here. I'm not going to save it, and I want to go to one called OMA curve fitting. Now this is tutorial number 9 in the manual. So if you go to the manual, and the best way is to go online now. We have the manual online. If you go help.vibetech.com, you can pull up this tutorial. Let me just go see if I can do that.